Hello, everybody. Let's get started. Thanks for coming. See a nice full room. I thought I might have frightened you all away with my talk yesterday. First of all, a little bit about me, my background. My name is Julian Hyde. I am an architect at Hortonworks. I've been working in open source for a number of years in database and business intelligence. My main job these days is working on Apache Optik. It's a project I founded. It's a query optimization framework, which is actually the engine that makes the Hive query, cost-based optimizer possible. A few years ago, I founded the Mondrian project, which is an open source OLAP engine. I'm still active in it, although not as active as I was. It's part of the Pentaho suite. And it kind of inspired a lot of the things that went into Optik in terms of wanting flexibility about where data comes from, optimizing interactive style queries, that kind of stuff. And I really realized that I needed more flexibility in terms of where data comes from. I'm also a committer on Drill, and I contribute to Hive, although I'm actually not a regular contributor to Hive, and a lot of the credit for this work that I'm talking about actually goes to John Pulakaran and Harish Bhutani, who actually did most of the work on the Hive team. I was assisting by fixing bugs in the Optik engine and giving them advice and so forth. In the past, I've really been doing database stuff. I was chief architect and founder of SQL Stream, doing streaming SQL. And before that, I was at Broadbase and Oracle. So I'm a database guy, but I'm gradually figuring out what this Hadoop thing is all about. I wanted to give credit to John and Harish because a few of the slides, in addition to doing the work, quite a few of the slides in here are originally by them. So, Hive, the kind of godfather of SQL on Hadoop tools, and it's not what it used to be. The joke is everyone benchmarks against Hive, and even Hive benchmarks against older versions of Hive. It's been undergoing extensive renovation recently, giving it a more modern architecture. And the performance and latency and so forth has improved massively. And that work is still going on. So stuff like, moving Hive to use the TES execution engine, using Yarn, using vectorized representations for data flowing through the system, introduction of ACID transactions, the work for that is going on now. Moving to cost-based query optimization is just one part of that, of making Hive more modern and a more flexible code base to develop and add future features to. So here's the, as I say, we're in the middle of a process. I just thought I'd just kind of show you the past and future releases of Hive and what features exist where. Hive 12 was released in October, and it was kind of, classic Hive from the perspective of query optimization. It was, all our optimizations were rule-based. The joins were basically executed in the order that they were written in the query and so forth. Hive 13, this cutting over to cost-based optimization in Hive, we really tried to get it ready for Hive 13. Which was released in April, and we got the bugs fixed, but it didn't quite make the deadline. So HTTP 2.1, which also released in April, but was from just a slightly different version of the code, it made it into HTTP 2.1. It didn't make it into Hive 13, but the patches are there, and they'll be accepted into trunk. I feel pretty sure in the near future. One feature that was added to Hive 13 that is still useful. It's not really part of this cost-based optimization work, but the ability to write old-style joins, that is, from table, comma, table, and Hive can figure out how to push join conditions down into the joins, even though you've specified it in the old syntax. It sounds kind of daft to be adding an old style SQL construct to Hive, but it helps with benchmarks, and a lot of tools generate, including my own tool Mondrian, I should say, generate joins in that old syntax. So a brief aside on what Optik is, because Optik is the engine that's making this possible, and also because this effort of moving to cost-based optimization, it's mainly about the effort of moving to a new engine. It's not about any specific optimizations, although we did add some optimizations. The main purpose is moving to a new framework, so it's going to be easier to maintain Hive and make it more powerful in the future. I'm actually having my house renovated at the moment, and it's a very similar process. You have to move out and undergo a lot of disruption just to end up with where you were at before. So it's actually pretty amazing that we got it going in such a short time, and there's a lot more planned in the future. So just a word about the engine. It's just become an Apache Incubator project. I've been working on it for a couple of years. And it's a framework. It does come with some built-in rules and so forth. But the idea is that you can use it to build a data engine. It is in use, and you can use it embedded, which is the way Hive uses it, or you can actually use it as a standalone engine. You can fire it up. You can log into it using SQLite or any JDBC connection. And you can use it as a kind of head on top of, you can use it as a federation engine. You can execute queries on CSV files or against Mongo or joining Splunk to MySQL or whatever, just using raw Optik. So it's, in that mode, it's pretending to be a database. Yeah, as I say, it's used in Hive now. It's also in use in Drill, and it kind of powers the SQL interface to cascading, which is called Lingual. And there's a wide variety of adapters, and contributions are welcome. We love to get people supplying new adapters so we can connect to new data sources. So architecturally speaking, this is a kind of simple RDBMS architecture, a simple single node RDBMS. And it stores its own data, it has its own metadata, it has a SQL parser, a JDBC client, an optimizer, and implementations of the algorithms like joins and so forth. Optik kind of strips that down, and all of the areas on the diagram that are white are supplied via SPIs, they're not part of Optik. So Optik doesn't store its own data, it doesn't have its own metadata, and it doesn't have its own rules. So you, the person that are using Optik to build a data engine, you supply that. It doesn't have its own algorithms to process data. At its core, it has a query optimizer, and if you like, you can use the JDBC driver and the SQL parser. When used in Hive, we don't use that. We just use the query optimizer part and some of the built-in rules. So this is kind of an overview of what the Optik framework has. The most important thing is the relational algebra. So these are Java classes that implement an interface, rel node, and kind of all the ones you'd expect: table scan, filter, which is a where clause. Project is what a select list does. It computes a set of expressions. Union, aggregate. There are others like sort and so forth. The list is intentionally fairly small because if you introduce a new one, you have to write a bunch of rules so you can combine them. And one of the great things about relational algebra is the set of built-in operators is very small. But you can add your own types of operations, and you can also provide your own implementation of them. For example, in the drill project, there is a drill project. There's an implementation of project using drills, mechanisms, and so forth. And that's part of the process of using Optik in a particular data engine. There's also things like physical properties, which we call traits, like whether a particular expression is sorted or not and how it's distributed. Again, you can add new kinds of physical properties. A physical property might allow a particular plan, like a merge join, to be possible. If a merge join is possible if the input is sorted. And if the input is sorted, it might be a lot cheaper to do something than if it's not sorted. Transformation rules are the other kind of core aspect of it, of what it does. So I'm going to clarify. Optik is a cost-based optimizer, but it has these things called rules. So that doesn't make it a rule-based optimizer. A rule it's, I had to name this class something, and rule is a pretty short word. It's a transformation rule, which means it takes a tree of a combination of relational expressions, for example, a filter on top of a filter, and it transforms it to something else. So if you've got a filter on top of a filter, for example, x greater than 5, on top of another one, which is y less than 10, you can convert that to a new filter, which is x greater than 5 and y less than 10. So you've combined two filters into one filter. That is an example of a transformation rule working. Now, that's not very profound, but if you get 100 of those, throw them into a bucket and stir, the optimizer starts doing kind of wonderful things. When you combine that with so the other thing the engine does is when it fires that rule, it produces a filter on top of it. It produces the successor, but it also keeps the original. It's not actually, by firing that rule, you're not saying this is better than that. You're actually just saying this is an alternative, and it keeps both alternatives. And as it fires the rules, it's keeping an ever-increasing list of alternative plans. Then the cost model comes in, and the cost model picks which is the best plan. Now, it's actually using the cost model at every step in the process to help it guide towards the best plan. But in principle, you can just imagine it generating all the possibilities. And the goal here, remember, is this is extensible. In fact, it's an even higher goal than that is we want people who don't write optimizers all day to be able to write these things. And that is a very demanding thing. To take an analogy, back in the day, people used to write parsers by hand. And then someone wrote a parser generator. And actually, people haven't stopped writing parser generators. I wish they'd stop. There's too many of them out there. Yak was good enough. But anyway, Yak and other parser generators make it possible to write a parser even though you don't know the details of context-free grammars or whatever it is that parser theory is based on. That's the idea here, is making this accessible, or at least reasonably accessible for people building data engines who don't want to become optimizer experts. There's other stuff on the screen. I'm going to pass over that. So after that brief interlude, back to Hive. How did we use this technology in Hive? So, well, actually, first of all, why are we going to this trouble of doing cost-based optimization? It's kind of an ease of use thing for users. We don't want users to have to specify their queries in great detail and exactly right. And we want the system to be more forgiving of how the queries are specified and to adapt better to the shape of the data, which the user, after all, may not know the exact shape of the data. They may not know which table is bigger than which. The most stupid possible user of a SQL system is a tool. I know I wrote one, and it generates some pretty dumb SQL. We still want that SQL to evaluate in a reasonable speed. So the optimizer has to provide the intelligence because the tool is generating often really, really dumb SQL. Stuff like being able to have view chaining, which is views inside views, being able to just deal with really, really large queries and not make big mistakes. So that said, this is the first version. The goal was to get onto a cost-based engine. The other goal was to demonstrate some concrete results, to show some improvement in some queries. And we chose one particular area to do this, which is automatically reordering of joins, so that it could make some optimizations based on joins being together in the parse tree. So let's just look at this is the pipeline of operations that happens internally within Hive. And this is kind of the strategy of how we slotted this into the process. So this is the, actually this is, I might have mislabeled this. This is the original query preparation plan where you parse SQL and it converts it to an abstract syntax tree. And the semantic analyzer validates that syntax tree, annotates it with stuff like type information. And then it goes and produces, it converts that into a plan. The plan is then, as part of the process of converting it to TES, it physically optimizes it by adding tuning parameters and so forth, and then finally submits it for execution. So, and the logical optimizer in, actually this is as it stands in Hive 13. The logical optimizer is working on that AST. So this is where I hope to get to, is basically replacing, we're still going to keep the SQL parser and the semantic analyzer, and use Optik for the optimization, working in Optik's representation, which is not an abstract syntax tree. It's not a it doesn't look like the SQL necessarily. It looks like relational algebra. And Optik is doing a series of steps based on that relational algebra. That's where we want to get to, and obviously there's a translator from AST into the relational algebra format. So what we implemented at this point is, well, kind of a roundabout, I think everyone would admit it's duct taped in some sense. The basic idea is to do join ordering, take the AST, do join ordering, and then basically emit an AST. So you can imagine that it actually generates a rewritten query that goes through the process again, and then goes through the kind of conventional optimization process afterwards. The cost-based optimizer is still adding a lot of value because it's doing the join ordering. And this allowed us to familiarize ourselves with the code, start moving some algorithms into Optik, but it allowed us to keep a lot of stuff running. So yeah. Okay, so these are the basics about how a query gets parsed, validated, and optimized, and executed. On the left-hand side is the SQL. It gets translated into a tree of relational operations. The bow tie shapes, for those of you who are not optimizer geeks, are join operators. And then the sigma is I always get this mixed up, a select, which means a where clause. And then the pi is a project, which means producing some expressions. And then at the bottom is an actual physical plan of how this might be implemented in TES. So if you kind of mentally rotate that thing to the right, you can kind of see that there's similar stuff going on, but there's a choice of, which order do we join R1 and R2 together first, or do we join, let's say, R1 and R3 together first? And what join algorithms do we use? So that's the job of the optimizer. So even in a three-table join, there are all of these various possibilities, all of which will produce the same answer, but they may have a very, very different cost. The job of the optimizer is, number one, to produce all of those possibilities, while preserving correctness. And number two, to assign an estimated cost to them so we can choose the best one. So this is, while renovation is in progress, this is actually the flowchart we use to figure out, are we going to invoke the new optimizer? For queries which are, because we, for example, don't recognize all UDFs, and because, for example, we can't operate if stats aren't available, we basically go through this process of figuring out whether to invoke the new optimizer or whether to just fall back to the existing process. This basically means that Hive users, Hive applications will continue to work as we're transitioning over to this. So if there's outer joins, sorry, you're out of luck, they're not supported in this release, we'll just fall back. If there's more than, if there's 10 or more joins, we fall back to the old process. These are all areas that are on our list to fix in future versions. Well, here we are. Okay, this is how Optik internally works. So on the left-hand side, we've got Hive plan coming in. It's converted into rel nodes, which are the relational algebra. And Optik internally has a queue of rule matches. So remember that a rule is something that matches a particular set of expressions. As the earlier example I gave is a filter on top of a filter. A filter on top of a join might be another one. A join on top of a join is a relevant pattern if you're interested in permuting the order of joins. And it applies the rules and it generates a thing called a rule match, which means I've identified these relational expressions match the criteria for this rule, but it doesn't actually execute the rule. Because if it did, that would generate some more rule matches and some more rule matches, and we'd never stop. The rule queue basically allows it to prioritize what it's going to work on. So it generates this queue of rule matches, and then it orders them by importance, which is kind of a heuristic that allows it to figure out how much good that rule is going to do. If that rule isn't going to do a lot of good, it goes to the end of the queue, and we might never get to it. Or we may get to it later on in the optimization process. Very important aspect of how Optik works is rel nodes are immutable. So when you fire a rule, that rule mustn't modify the internal state of that rel node or any of the rel nodes in that rule. It must generate new rel nodes. And when it generates them, it actually canonizes them. It registers them internally. And there's a significant chance that that particular pattern has already been generated, is already known. That's kind of an interesting, that's kind of a big deal. That's a good thing for the optimizer because it means that it's just discovered that this expression is equivalent to this other expression, which means that they're now in an equivalent set, which means the cheapest way of doing this is also sufficient, is also the cheapest way of doing that. And Optik internally is basically maintaining these sets, these equivalent sets of relational expressions which are known to produce the same result, but maybe producing it in different ways. Also part of this is a cost model, and there's a couple of aspects to the cost model. One of which is well, cost and statistics are two related ideas. The cost model is how much resources will this use to execute. Statistics are how many rows do we think are going to come out of this, which columns are unique, what would be the selectivity if we evaluated an expression such as x greater than 5. In other words, if we evaluate x greater than 5, what proportion of rows are going to come out? There's a whole variety of statistics, and in fact, the statistics model is extensible. So if the drill guys decided they wanted to add extra statistics for drill, they could without recompiling Optik. Okay. Is this all making sense? Okay. Join reordering. So this is the main optimization we're interested in here. And the way we achieve it is by adding, I think it's just 2 rules. I think it might be 3 rules, 2 of which are left and right variations of each other. So one is a very simple swap join rule. Given a join, it's a very simple rule that only matches one thing. Given a join node, apply this rule and it just generates the thing flipped around the other way. You might say, well, is that rule going to fire forever? Is it going to generate the same thing? It's going to generate B, it's going to permute AB, and it's going to generate B join A. Isn't that rule going to fire again and generate AB? And actually it does, but it recognizes that what it's produced is the same as something it already has, so it now stops. Thank goodness. The other rule here is push join through join, which basically takes a tree, and if the tree is A join B underneath C, it now permutes it to A join C underneath B. Those 2 rules are powerful enough to generate quite a lot of join permutations. They can't, about halfway through the process, John came up to me and said, do you realize this thing can't generate bushy trees? And I said, John, what is a bushy tree? Basically, a bushy tree is a tree which branches on the left and also branches on the right, as opposed to being left deep or right deep. But it still generates quite a large number of permutations and is still useful for a large number of common query cases. And support for bushy trees is something we intend to add in the future. You put these rules together and unleash the optimizer, and it generates a lot of combinations. So to summarize what we've done here, I didn't mention we have a simple cost model here. We just basically measure the number of rows. We're not trying to be clever about number of I/O or the amount of network I/O or disk I/O or CPU cost. We just use the number of rows. It's a reasonable metric. It's not perfect. Something we'd like to improve. All other operators are assumed to have a tiny cost because the purpose of this optimization is just to get the join ordering right. We don't have, actually figuring out how many rows are going to come out of a join is a difficult thing. For one thing, because statistics are often approximate. But we use an estimate of the selectivity of the condition, which means we maybe don't know, we're maybe not taking into account skewed distribution of the columns that are being joined. There's an opportunity there for adding better statistics, for example, a histogram of the distribution of the values of the columns that are being joined. But it'll do for now, and I'll show you later some queries that have some improvements that we've made through this. I've mentioned the limitations already. We only support some core relational operations. We don't support all functions, and we don't generate bushy trees. Let's look at some queries that we applied this to. These are from the TPCDS benchmark. This one is a join over 5 tables. And before we used cost-based optimizer, it was doing after we'd used cost-based optimizer, it was basically able to combine all of them into a shuffle map join. I should stress I'm not a complete expert. I'm not an expert at all on how Hive does stuff. So if you have any questions about this, Harish is in the front row. But Harish tells me this is an awful lot better. yeah, I guess the amazing thing about it is that Optik is ignorant of what Hive does, but it still, given the rules that Harish and John supplied, it was able to do this. And here are the results. So based on, I should say this is like TPCDS query 50. This is not TPCDS query 50 because we wouldn't be talking. If we run something like TPCDS query 50 on 3 months of data, the cost-based optimizer plan runs approximately twice the speed. If we actually use a year's worth of data, the query didn't finish within a reasonable time before or at least it didn't. It took more than 10 minutes, and we lost patience and hit Control C. Our 1 year of data took about the same amount of time as 3 months of data. And at the bottom you can see various the cost estimates that the optimizer came up with. I don't actually know how close to the truth these are. These are just estimates that allow it to kind of rank the various options. But as you can see, the different join orderings have very different costs. TPCDS query 17, which has, I don't know, a lot of tables in it. So obviously, join ordering is a big issue. So amazingly, it was the cost-based optimizer was able to combine 1, 2, 3, 4, 5, a 6-way join into a shuffle and map. Previously, it was doing a big. Actually, I don't know what I don't know the details about this. Ask Harish. So there's more work to do. We've got the infrastructure in place, and we've got a long list of things that we want to do next. Outer joins. I'm working on something which will allow us to scale to an unlimited number of joins. We can't actually, no query optimizer can actually consider the whole search space of, let's say, a 50-way join, because it's an exponential size search space. So I'm working on something which will use some heuristics, a greedy algorithm, to come up with a reasonable, a few combinations of joins that are likely to be close to optimal, rather than using rule firings to generate, all of the combinations. And then, so a lot of this is basically expanding our support to the full Hive SQL, all expressions, all data types, and so forth. We want to do join algorithm selection. So right now we leave that to the, we do join ordering, but we leave actual selection of join algorithms to the conventional Hive optimizer. We'd like to do join algorithm selection, and that means we have to have knowledge about whether the data is sorted and how it's distributed, how it's bucketed. So we're going to introduce a trait so that we can a physical property so that we know how the data is ordered, and then the various rules for join operators will be enabled if the data has those physical properties. Trait propagation means if we introduce sortedness, we need to let it know that if a sorted collection passes through a filter, for example, the output of that is also sorted. The ability to, for example, say, I would like something like this but sorted, and pushing down that requirement down the tree to tell the underlying sources that you'd like a sorted version of this. Proving the cost model, adding more statistics. Statistics are kind of like a virtuous cycle. That once you have join rules that can use statistics, there's an incentive to gather more statistics, by which I mean different kinds of statistics. You know, the example I mentioned earlier was a histogram of column values. Stuff like constant reduction, if you can figure out that x greater than 5 is always false because you know about the, maybe from the histogram, or maybe you know something about based on the partition map, then you can start pruning away parts of the tree. My favorite, as you all know, if you came to my talk yesterday, is materialized views. I think they are you know, an opportunity for, you know, many orders of magnitude improvements in query performance. And kind of just dealing with the, we'd like to move more and more of the logic into Optik, because of the way Optik operates. You know, it doesn't modify its the expressions as it's working on them. It tends to make software engineering easier, because if you add a new algorithm for X, you're less likely to break Y, and that's been a kind of maintenance problem in Hive, that the order of the different parts of the query preparation are very sensitive, because the abstract syntax tree is modified while the query is being prepared. So that's all I have. We have about 3 minutes for questions. So, yes.
Will you support any kind of hints?
The question is, will we support any kind of hints? I don't know. Does anyone in the Hive developers in the room have an opinion about hints?
Should we, since with this, it looks a lot more like a relational database and a lot less like, say, Hive 0.6 version or 0.7, which was a batch SQL query against files kind of thing. So should we look at this and see this, that Hive is basically going into the general direction of, say, becoming something like Vertica, Teradata, what have you, pick your favorite MPP relational database that runs on top of HDFS?
There's a lot of good things in relational databases. And I mean, SQL, SQL makes it look like a relational database. Standard SQL is good. I mean, the traditional extensions to SQL in Hive are still there, but Hive now supports standard SQL, and that is, you know, unquestionably a good thing. The execution framework underneath Hive, which is, you know, Hadoop, Tez, is unquestionably part of what makes it attractive. You know, the fact that you're reading files out of HDFS rather than reading it out of, you know, a proprietary database vendor's format. So, yeah, our goal is to bring in the good things about relational databases, and we don't apologize for that. I don't think it's, you know, Hive is more powerful and more flexible with this stuff in than it was before, and you know, we think it'll be faster. So, yeah, I don't think there's any regret that we're moving in this direction. Oh yeah. Yes.
Do you see UDFs when they come in that supported to influence that cost-based optimizer?
Sorry, can you say again?
When you support UDFs, do you see them influencing the cost-based optimizer?
Does what influence the cost-based optimizer?
UDFs.
Oh, currently no, because yeah, we don't support them. I mean, we pass a right now, Hive operators, like, you know, even something like plus, passes through Optik as a user-defined function, and Optik doesn't understand what it is. You know, ultimately, we will support table functions and so forth, And that'll be interesting, how the optimizer is able to understand table functions and whether any metadata can actually propagate through the table functions. I have some ideas how to do that, but that'll be interesting. One last question. No last questions. Okay. Thank you very much.